Okay, so last video of this set, just quick review to make sure that we're okay with everything that we've been doing so far. Okay, we've got 3 different things that we've been looking at. Reflection. Remember, reflection is the bouncing off of the waves from a surface. Here, let's look at it this way. We've got reflection, which is where we have a ray that's bouncing off, right, of a surface. The angle of incidence is always going to be equal to the angle of reflection. Of course, we're always looking at compared to the normal. You've got your wave fronts and you've got your rays. The rays are the direction of the energy transfer of the wave, which is this way and bounces off and goes this way. And the wave fronts or your wave crests are always perpendicular to that. Okay, so this is a good example. This says it's a metal strip placed in water, but it could be a mirror and light bouncing off of it. It could be a wall and sound bouncing off of it, right? All of these waves are going to follow the same properties, the same principles, okay? So that's wave reflection. Wave refraction, okay? Wave refraction is this idea that when the medium changes, either to a different medium or you change the properties of the medium that you're in, it's going to cause the waves to bend. So this nice straight wave is now becoming slightly bent as it goes in. And that's what you're seeing, when you look in a glass of water and you see that the straw looks like it's been displaced or bent, right? You've all seen that, where you've got your glass of water and you got your straw, and then all of a sudden it looks like your straw is over here. Well, that's because of the refraction of the light, because the light is being bent inside the water. So anyway, so that's refraction. We talked about that and how that happens in different mediums, and that different wavelengths, therefore different colors, bend in different ways. So we kind of got that idea. We've got diffraction, right? Diffraction is the spreading out, which is what we talked about in that last video, and the spreading out of waves. Talked about Huygens principle, those types of things. All right. Remember, deeper water means that you're going to have longer wavelengths. This is thinking back to the refraction. Sorry, this is something that students often ask about and they get confused about. Deeper water means longer wavelengths, which means that the velocity is faster. Okay, and in some ways that's counterintuitive, because you would think as the water gets shallower that the waves should be able to move faster, but that can't work. There's some things with conservation of momentum and some other things that are in there that we're not going to worry about. Okay, but recognize that for the case of water, it's actually opposite of what we would expect. Deeper water means faster waves, means they have a longer wavelength. Okay, the other thing that I wanted to make sure that we mentioned is what we mentioned in the very last slide of the last video, which is for diffraction. Remember that, and not diffraction, just in general, for energy is proportional to frequency. You double the frequency, you double the energy, and energy is proportional to amplitude squared, okay, which means that doubling the amplitude is actually going to quadruple the energy. All right, so those are things that I want to make sure that we remember as we move into our next idea, which is polarization. Okay, now for polarizations, the first thing that we need to recognize is what exactly is an EM wave. And we talked about that at the end of one of our videos a couple of classes ago. Electromagnetic wave, and I mentioned this, is an electric field and a magnetic field that are propagating through space. Now, because it's a field, it doesn't actually need a medium. That's why it can go through a vacuum. That's why it moves fastest in a vacuum, because it doesn't have electrons absorbing and re-emitting, and it's not bouncing off things. It's just moving as fast as it possibly can through space. Now, what we see here is an image. This is obviously not exactly right, but the electric field and the magnetic field are perpendicular to each other, so they're not affecting each other, right? And this wave, you can see the idea of the wave, that the electric field here gets greater, and then it decreases, and then it gets greater and other. So you can see the idea of why it's treated as a wave, and indeed it will follow the properties of a wave. It's also going to follow some properties of particles as well, but we're not going to get into that too much right now. We'll do that when we get to atomic and nuclear physics later, but I just want to make sure you recognize that I'm not lying to you, that it is going to use some properties of waves, but it's also going to have some properties of particles later. Okay, so just this idea, it has electrical magnetic fields. When light is generated, it's not polarized. Okay, now what does polarized mean? Polarized means that you orient it so that all of the electric field waves are in the same direction, right? This picture that we have right here is polarized, okay, because all of the electrical waves are going in the same direction, right? They're all up, down, right? All the magnetic fields are going right, left, right, left, right, left, okay? Let me show you, okay? So you see here at the beginning, going in, and the beginning is down on this side. We're moving back into the page, going that way. Okay, so when electromagnetic wave is created, it is unpolarized. You see how it's kind of, right now we are only looking at the electric field. Okay, we're not going to look at both electric and magnetic all the time. We're just going to look at one field. Okay, so we're looking at this electromagnetic wave, and you can see how it's going side to side. Now it's going up and down. Now it's going diagonal. Light is unpolarized normally when it's created. Okay, but we can do something with what we call a polarizer, and I wish we were in class right now because I could show you these. But I promise, as soon as we get back to class and we're ready to start doing some things, we'll spend the first couple of days just looking at these things and understanding how it works in the real world. You could probably search up some videos on YouTube and you'd be able to see what polarizers actually do and what they look like. If I was even back in Shenzhen, I'd make videos of some of the things that we have back there. But the reality is that we don't, and so we'll have to work with what we got. A polarizer will take, it only allows light or components of light that are in one specific direction to go through. Right? So this specific polarizer we've lined up so that it only allows light in this diagonal direction to go through. So this wave right here that is in that direction, it's going to all go through. Okay? This one right here that's vertically up and down, well, we can create an axis like this and a component of this light, right? Because a component will be in that direction and a component will be in the perpendicular direction. The component that's parallel to this will go through. Okay, so a part of this middle wave will go through. A part of this bottom wave will go through. So some of the light will go through. Now, because it's components, right? If we have light going through in different directions, okay? Some of the light, on average, half of the light's going to go through. This is a neat thing, is that if you have unpolarized light, 50% of the light is going to make it through our polarizer because we're allowing all light that it has a component of that. Half of it will be vertical, half of it will be horizontal, or whatever direction our polarizer is pointed in, and 50% of the light will make it through a polarizer. Okay, and this is going to be an important idea later. But this idea of being able to polarize the light so that the light's all in the same direction is going to be kind of an interesting idea, and we'll look at why that's helpful later. Okay, here's an idea, kind of how a polarizer works. I kind of don't like it because it's actually the opposite of how it works. But look at this. So you've got a guy, he's shaking a string up and down so that it has vertical waves. The vertical waves obviously are going to go straight through this fence. The fence has vertical railings, and so as long as your wave is going up and down, it's going to go straight through the fence, right? If you turn the fence sideways, what's going to happen when the wave gets there? Well, the wave is going to hit the top, it's going to hit the bottom, and it's not going to be able to get through. And so the wave is going to stop, and it's going to be flat on the other side. Okay? Now, a real polarizer is actually the opposite. Okay? A real polarizer has these long strands of molecules in it, and if the molecules are this way, then it absorbs all the light that is horizontal. And so actually only the vertical light gets through. So it's the opposite of what it seems like from this model. Like I mentioned in the last video, models are meant to simplify things, is to help us understand However, they generally have some kind of issue, some type of problem with how it works, okay? So, but recognize usually when they tell you about a polarizer, they're going to tell you what type of light transmits, what type goes through. So they're not telling you about the molecules, they're not telling you about the rails of the fence. What they're telling you about is what type of light goes through. All right, so hopefully over the next couple of slides, we'll be able to get a better idea of how this polarization works. This is what I was just talking about, right? If the molecules are vertical, then it's going to absorb the vertical light, and only horizontal light will go through. It'll have a horizontal polarization axis, okay? If the molecules are horizontal, then it's going to absorb all the horizontal light, and only the vertical will go through. Okay, so recognize that it's only taking out the light that has that component. So if I had some light going through at an angle like this, it's going to take out the horizontal component, but the vertical component, right? We talked about vectors a little while ago. The vertical component will make it through, okay? And for unpolarized light, any type of polarizer, you're going to get 50% of the light that goes through. Okay, as long as it's completely unpolarized light. We'll talk about what happens in other situations shortly. Okay. All right. So another idea that I need to mention with polarization before we do a little bit of math with it is this. When I have a light beam that's going to be reflected off a surface, right? So I've got maybe water down here, and I've got air up here. So the light is coming in, right? We have an unpolarized beam, which means that we've got, the light's going in all directions, horizontal, vertical, coming in and out of the page, all directions, okay? So it bounces off of this surface. Two things are going to happen, okay? One is that we're going to get some refraction, right? Because we're going into a new surface. The light is moving slower, therefore it's going to move towards the normal, right? The other thing that is going to happen is that we are going to get some reflection, okay? When the light reflects off the side, obviously the angle of intersection, incidence has to equal the angle of reflection, so those are going to be the same. The polarized beam, the reflected beam is going to be polarized. It's going to be polarized because of how it's reflecting off of the surface. Okay, now this is a kind of an interesting idea because of how it's bouncing off the surface. Then, because it's bouncing off the surface horizontally, then we get a light beam that is polarized horizontally. If you've ever had sunglasses that were polarized sunglasses, the point of polarized sunglasses is they get rid of the glare. Now, what is the glare? Well, the glare is because light is coming down and it's bouncing off of the car hood or the windshield or whatever it is, and when it bounces off of that, it has horizontal polarization. Okay? Now, most other things are polarized in all directions, right? But the glare, the stuff that's reflecting directly off that surface, that is going to be polarized. And so when you put on the glasses, it does decrease 50% of the light, which is why everything's not as bright, but you'll notice that it can actually take away that glare 100%, because the glare is coming off of a horizontal surface, and so the light is polarized horizontally. So if your sunglasses block all horizontal light, right? So automatically as the light comes in, you're blocking 50%, because that's what polarized lenses do. They block 50% of the light. But if it's set so the transmission axis, so you're blocking the horizontal light and only letting the vertical through, the blocking the horizontal is going to block all of the reflected horizontal light. And so the glare is going to be completely gone. Look at that next time you're wearing polarized sunglasses. If it doesn't do what I'm talking about, then you bought a fake pair of glasses and they're not really polarized. But polarized lenses are pretty easy to make, so if it says it's polarized, it probably is. You should be able to see this, okay? We'll talk about those polarized lenses again here in a little bit. But yeah, this is one of the ideas that I want to make sure that we talked about. Notice that the stuff inside the liquid is partially polarized. We're not too worried about that at this point. We're not really going to go over that a whole bunch. Really, what we're concerned about is this idea right here, that when it reflects, it's going to be completely polarized in the plane of the reflection, and we can obviously block that with a polarizer. Okay, lovely. Let's look at the next piece. Okay, so the next piece is actually going to introduce us to some calculations and to how we deal with this type of thing, and we'll talk through how to do this. Okay, so this is dealing with two polarizing lenses. Okay, one is called the polarizer, the other is called the analyzer. Okay, so what happens here is that we have light that's coming in. Okay, then you have one polarizing lens that we say is the polarizer. Okay, the purpose of this, because when the light comes in here, the light is unpolarized, right? It's going in all directions. Okay, but then when it goes through here, let's say it's a vertical transmission axis, then as the light comes through, it's all going to be vertical. Okay, so this is what's called the polarizer. Okay, then we're going to put a second one here that is going to be at some other angle. Okay, now depending on what that angle is, this one is called the analyzer. Okay, and the reason it's an analyzer, because usually we're going to have something in between happening that's going to change the direction of the polarization. We're not going to worry too much about that, because that's usually chemistry. I am going to show you an image of it here in just a second. Okay, but I do want you to recognize that there's a purpose for why we have this polarizer analyzer. What if we had an analyzer that was a horizontal transmission axis? Okay, this is interesting, because this light, which was at 100% intensity, goes through the polarizer. Remember, when we have non-polarized light being polarized, it becomes 50% intensity. Okay, now this one now is polarized. Okay, it's vertical. What would happen if it goes through a horizontal transmission axis? Well, those two are perpendicular to each other. There is no component of this in the horizontal direction, which means if this vertical light goes through a horizontal polarizer, you would get 0% of light going through. 0%, because there are no horizontal components to vertical light. They're completely independent of each other. Okay? If you had two pairs of sunglasses, okay, sunglasses should not be vertical, they should be horizontal. If you had two pairs, right, and you were to take one of those pairs and hold it sideways, right, so you turned it like this, right, so it's are going this way. So you have one that is now horizontal, the purple one, and one that's vertical, the green one. You would see that those two lenses would block out all light. I want you to try that. If you can find two pairs of polarizing sunglasses, maybe you got to go to the store. Go to the store and find some lenses that say they're polarizing lenses and hold them at 90 degrees to each other. And I want you to see that those two glasses will completely block out all the light. You won't be able to see through anymore. Now, as you rotate them, it'll start to let light through. Because as soon as I rotate this analyzer here, and I don't think I can, I guess I can do that here. I wish I had an eraser. This keynote thing is going to drive me nuts. I guess I should import it to something else. Oh, there it went. Oh, no, okay. All right, so we're going to take away the direction of our analyzer there. So what if the analyzer was at an angle here? Right? Okay, so now we had 100% of the light here. Goes through the polarizer, it's now at 50%. Okay, now it goes through an angle. Now, because it's not horizontal, then that means that there is a component of light that is that would be allowed to be transmitted through here. So that percentage here is going to depend on this equation right here, which has been up in your face the whole time that I've been talking and blabbing on and on and on. Okay, so we can calculate based off of the incident light. This is the incident. Okay, and that can be an intensity. It can be a percentage, right? We can start with 100% and go to 50%, right? This is the after the polarizer. Okay. This, remember, doesn't work if the light isn't polarized. This is only incident polarized light. Okay. And the angle is the angle between the actual polarized light and the axis of transmission here. Okay. What would happen if the analyzer was like this, if it was vertical? Well, that would mean that all of this vertical light would be able to pass through. And so no light would be lost here. Okay, so I wanted to make sure to mention that because none of the light will be lost. If you have vertical light going through a vertical analyzer, which is a polarized lens, that none of the light will be lost because you're only losing light that is a perpendicular component to the transmission axis. If all of the light is parallel, then all of it's going to go through. None of it's going to get absorbed. Okay, so we have 50% of the original light here. We still have 50% of the original light there. And so you should be able to see that if you play around with those polarized glasses at the store as well, is that if you hold them in the same direction, that it should be almost exactly, and here I am sitting holding my sunglasses and playing with it, looking at my eyes. You can't see that. But if you hold it, it should look almost exactly the same with one lens and with two lenses, as long as they're oriented in the same direction. The only time you're going to get something different is when you rotate them so that they are 90 degrees perpendicular to each other, or any other angle will cause something in between. All right, this is the equation that you'll be using tonight, okay, to help you. This is the incident intensity. This is the angle between the angle of polarization and the angle of whatever the analyzer is. Okay, and so that you should be able to kind of figure out some problems with that. I do want to show you
first we need to know about plane polarized light. Is just
the light on the left is just regular light. The oscillations are all over the place. But if you pass it through a plane polarizer, the black bars represent that, then you're left with plane polarized light, which is coming out on the right. This oscillates in only one direction or one plane. Now, once you have this plane polarized light, if you pass it through one of the stereoisomers from a pair of stereoisomers, then it will rotate the light coming out by a certain angle. And if you pass it through the other stereoisomer from a pair of enantiomers, it will rotate it the other way. And so a polarimeter detects these rotations and can identify the isomer you have.
All right, so that's a chemistry application of what we're talking about here, right? So you have some light bulb, light's coming in. You have a polarizer, so some type of, let's say we polarize it to go vertically, okay, and the light comes through, and the light before is in all directions, right? Unpolarized light. When it comes through, it's polarized vertically, okay? All the light is polarized vertically. Now we're going to send it through this chemistry thing, right? Which, if you're in chemistry, you may understand what a stereoisomer is at this time. If not, then don't worry about it, but it depends on the molecules and whether the molecules are right-handed or left-handed. Again, don't worry about it at this point if you're not in chemistry. If you are, you'll get it at some point. So the light goes through, and because of the molecules of this stereoisomer, whatever the chemical is, when the light comes out, it's no longer vertical. It's still polarized, but it's polarized at a specific angle. And by taking my analyzer and finding out at what angle I need to turn it, okay, either to completely block the light or to allow all the light to go through, I should be able to figure out what is the angle of rotation. And the angle of rotation is going to have, some type of connection to the concentration of my chemical. So I wanted you to see why we care about this and what we can actually do with it. This is polarization. Yeah, it's cool for sunglasses, actually for 3D movies, all about polarization. We can talk about that in a second, but 3D movies are that way with polarized light. But this idea of being able to use it to figure out what the concentration of a specific substance is, right? That's a chemistry application. So lots of different ways that we can use this idea of polarization. Okay. All right.
Okay.
All right. So just really quick, I do promise before I go to the last slide, I'll talk about a little bit more with this. But can you polarize a longitudinal wave? And take a minute to think about it. Pause it if you need to. I'm going to give you my answer right now. The answer is no. You can't polarize a longitudinal wave because remember, in a longitudinal wave, the energy is traveling this way, and the particles are moving back and forth that are parallel to the direction of the wave. So if I try to absorb them, nothing's going to happen because they're moving this way. They're moving in and out. They're not moving either in the direction or perpendicular to the direction of the transmission axis. So longitudinal waves, i.e. sound, cannot be polarized. Okay? Now, don't be confused because sometimes they ask about radio waves. And people sometimes say, oh, well, radio waves that's where I'm getting the sound from the radio. Well, no. A radio wave, remember, miv, ux, juk. Radio wave is a light wave. So radio wave is a transverse wave, and I can polarize a radio wave. In fact, if you ever had an old radio or an old TV, or you might watch a TV show where they're watching an old-fashioned TV on the TV, and they have these little antenna things sticking out, and sometimes they grab them, or maybe sometimes they have like a hanger up there or something. Sometimes they have to like take it and fiddle around and bend them. Well, the reason why is because the antennas have to be parallel to your radio signal, right? The radio signal is a polarized wave. If you are not parallel to that radio signal, then you're not getting the best signal possible. You're only getting, remember that formula, I equals I naught cosine squared of theta. You're only going to be getting a part of that wave, and so you're not going to be getting as good a transmission as you'd like. And so by playing with that, you may see an old movie where they're up on top of the roof playing around with the antenna trying to get a better transmission. That's what it is. It's because those radio waves are polarized, and because they're polarized, you get a better transmission in one direction than you do in any other direction. All right. I do want to take just a minute to talk about 3D movies, just because that's an interesting concept with this polarized lenses. When they first started 3D movies, the original ones had these glasses, and you may have seen these before. Had these glasses where one lens was red and the other lens was blue. So basically you could see red, you could see blue, and you could see black. That was it. The combination of the red and blue was kind of a blackish color. The way it worked is you had one picture that was red, you had one picture that was blue, and so this allowed you to see only the blue light because the red light was all being absorbed. This one allowed you to see only the red light because the blue light was being absorbed. And so one eye saw the blue light, one eye saw the red light, and your brain then interpreted that as a three-dimensional image. Just like your eyes right now see two different images. You don't believe me? Take a look at something off in the distance. Close one eye and look at it. And then switch your eye. Close the other eye now. and look, you should see that everything moves. Do it with a finger in front of your face. The finger's going to move from right to left as you switch from one eye to the other. And you can't see me right now, but I'm switching my eyes back and forth because I'm seeing things move. That's why things have a three-dimensional image, is because your left eye sees one thing, your right eye sees something different, and your brain puts that all together. Your brain is amazing. Okay, I make fun of biology a lot, but there are some really neat things in biology when you put the physics with it and when you put the chemistry with it that tells us why these things happen. The human body is amazing. But anyway, so that's what's working when you see three-dimensional, when you see space. Trying to catch a ball with one eye closed is much more difficult than trying to catch it with two eyes open. You may have tried the pen cap thing, right? Take a pen, pull off the pen cap, hold it behind your back, close one eye, and then bring both hands in front of you and see if you can put the cap on top of the pen with one eye closed the whole time. Chances are you can't do it on the first try. It takes you a couple of tries. The reason is because you don't have the two eyes seeing two different things, allowing your brain to have that three-dimensional spatial image. So that's how they used to be done. Okay. Then they came up with this idea of, well, we just need to create a screen that allows us to show polarized images. And so then they had these glasses that one polarized light vertically and one polarized light horizontally, because now they could do any color they wanted, right? The problem before was that it had to be red and blue, and that was it, red, blue, and black. Now you could do any color as long as you had two different images being reflected off the screen. One polarized vertically and one polarized horizontally. And that took a very specialized screen, right? Because most screens are going to polarize everything in a very specific direction. You needed it to be able to be polarized in both directions so that one eye is seeing the vertical light and one eye is seeing the horizontal light, so that your two eyes see different things and therefore you get a 3D image. Now, if you go to the theater nowadays, this may be the case, but chances are it's not even that. Now they use something which is called rotational polarization, which means that the light as it's traveling is rotating in one direction or another. So it's polarized, but it's polarized in such a way that it's constantly rotating in one direction or another. The problem with this vertical horizontal is that it only works if you're holding your head perfectly horizontally. If you turn your head to the side a little bit, then each eye is going to see a little bit of the other, because you got this vertical light coming in, you got the horizontal light coming in. But what if your glasses, you lay your head on the shoulder of your boyfriend or something, and your glasses are now like this, right? So this one now is going to be getting some vertical light, but it's also going to be getting some components of the horizontal. Same thing with the other one, and so you don't get the image very well. If your eyes are spaced differently or something like that, right? All that stuff can cause problems. Now, if you have lenses that allow you to do, and this is much more complicated, this isn't as simple as what we were talking about before, but if you have glasses that allow you to deal with this rotational polarization, then I can turn my head to the side, and the rotation is still the same. And so even when I turn my head to the side, or if one eye is higher than the other eye, or something silly like that, I can still see a 3D image. So anyway, I think that's a really neat application. If you go to like a theme park or something, I've seen both of these. If we do our Disneyland trip, or at some point if you go to Disneyland, Mickey's PhilharMagic uses glasses like this. Where it's linear polarization. If you do Iron Man, then the polarization lenses are rotational, and so if you put them in front of each other, they're not going to block out the light, because it has to do with the rotation of the light, not the lens itself. So anyway, some really neat things there, neat applications, sunglasses, all that kind of stuff. There's actually a whole lot more, but this is what we're going to have to end with today, because we're just about done. The last thing that I wanted to do today, just because it's a good thing for you to do, is I want you to define simple harmonic motion. Okay? So go ahead, pause the video, take 30 seconds, a minute, and try to write out a good definition of simple harmonic motion. The reason for this is because this is a very, very common definition on IB exams, and I want to make sure you've had as many opportunities as possible to find this, and I don't know that we've done it enough in class, or that you've done it enough in your reading. So just want to make sure 100% that you're okay with this idea, okay? All right, so hopefully you paused it. If not, do it now. But here is the answer or answers. Either one of these is fine. Okay, simple harmonic motion. The force on the object must be proportional to its displacement, and the force on the object must have a direction opposite to its displacement. Those are the two things that are necessary. Or you can talk about acceleration instead of force, because we do know that F equals ma, and so if it works, the mass, of course, isn't changing, so whatever applies to force also applies to acceleration. But this really is the definition you want to use. Okay, I know a lot of people like to say, well, the period has to be constant, the amplitude needs to be constant, the period is independent of the amplitude, displacement, velocity, and acceleration have sinusoidal relationships with time, right? Those are all things that people remember, and those are good things to know. But as far as a definition of simple harmonic motion, this is the simplest definition and the one that they want you to have. This is the one that is always in the mark scheme, and 99 times out of 100, this is the one that if you just mention these two things, you got full credit. Okay, it's going to be a 2-point thing. This is it. So the force on an object must be proportional to its displacement and opposite the direction of its displacement. All right? Okay, that's it for this video. I'm done. I imagine you probably are too.